also going to mess around with photos. In particular, a photograph that in itself may not look all that interesting, just a block of plastic or perspex, but I'm going to use it to demonstrate the refraction of light and do a few calculations and subsequently use Snell's law to work out, calculate a refractive index. See how we go. I won't demonstrate all of it. I've quickly got some of these things caught onto a PowerPoint, and John has shown you some of the key things already. But importing the image, if I'm looking for refraction of light, I can obtain a suitable image either by experiment, which would be the preferable method certainly, or the internet. In my case, I actually admit I did the latter, but I'll show you that. It's easy enough. Google Images. And then, as you've already seen, using the Connect software to place the image on your handheld and set it as the background. Very important then is to set the window settings to square, and if you forget that, you might end up with some really weird angles, because obviously the angles that you're measuring on your screen will look a little different, or the mathematics might give you the correct angle, but you'll look at that and see it doesn't look like the angle that's on your screen. A quick way to check that, by the way, I often throw in, say, y equals x, and students see, okay, does that look like it's running at 45 degrees to each of the axes? Yes, we have a square screen. The new quick plot and equation feature is just brilliant for quickly grabbing the, in this case, linear equations. Or alternatively, you could just locate 2 points and use a 2-point formula to get your equations. The ones that are going to be important to us, and you'll see the image shortly, a linear equation representing the face of the block, which is a straight line, the normal, and I used a point gradient formula to find that. The gradient, of course, was the negative reciprocal of the face, and the point I used trace to locate the point where the light ray struck the block. I constructed the incident ray, the refracted ray, used this formula to determine the angle between them, so the tan of the angle being the difference between the two gradients of two lines, divided by 1 plus the product of the gradients, and I had to do that for angle of incidence and angle of refraction, ultimately substituted into Snell's law to determine the refractive index. Now, thrill seekers, while you're quickly taking notes on all this, I should just remind you that we will be giving you this PowerPoint. I think Daisy may have mentioned you get this PowerPoint to take away at the end of the webinar. I always think it's quite important that people have something to take home with them from a webinar, even if they are sitting at home to do the webinar. So here I am grabbing the image. I just simply typed refraction into Google Images. I thought the one top center looked good. So you've seen how the drag drop thing works to place it on your calculator, and there it is set against axes that are square. And at this point I'm going to swap across to an emulator to show you some of that. So here's the same thing in my emulator, and to work out say for example the equation of the face here. Actually, I've got a few. I'll just switch one. I'll do the last one for you. So I've got a few of these switched on. No, I'll do the first one for you. Let's do that. Let's go Stat. We'll go across to Calculations. You can either go down to the bottom of the list, or you can cheat and click up, which of course will then give you the bottom of the list. I'm going down here just to show you. So quick plot sounds good. Let's run with that. And we'll place our 2 points. Hopefully this might work a little quicker than your parabola. Oh, no, we raced off the edge, didn't we? And so we've got one. And the other one that I thought I'd just like to look for some more critical points. So I actually looked for the point where, or you can put, of course it only takes 2 points for a straight line. Why not go with extra? And I looked for the point where our incident ray, oh, by the way, our light ray is coming from left to right. So there's our incident ray on the left that we're looking at. And with a little bit of patience, I locate this critical point here. And as John pointed out, the values x equals negative 1.95 and y equals negative 2.44, etc., are being stored into those memory locations. I use another piece of technology at this point. I actually store it onto a piece of paper. You remember that stuff? And then I just simply use the point gradient formula to calculate the angle of, the equation to the normal. So what I want to do now is, I guess, enter that point and fit an equation. As John's already shown you, we can select which regression model we want. I like linear. And off we go. And it will invite me to store this now. Now, I'm going to store it down into, I'm going to store it into Y5 because the first time I did this was in Y1, and I'll keep that for the calculations that I have already set up. But normally you just put that into your first function. So let's just take a look in the function editor. So down here at Y5, this is the one that we just calculated, and as you see, it's fairly close to the one that I did earlier on. To calculate the equation of the normal, I would take its gradient as being the negative reciprocal of negative 1.094, and then use the point that I indicated earlier to then use point gradient formula. There are other ways of doing it. John, when we were talking about this before, suggested we could construct a line along this face, which of course gives us the gradient, and then just by trial and error move it down to here by adjusting the y-intercept. That would be a valid approach as well, and all these things are I believe, valid mathematical approaches of investigation. So let's just switch.
And that'd be a nice thing if we're doing this as an investigation for them to write up in their, during their analysis.
Yeah.
Of how they actually did do it and their assumptions that they made and different approaches. Again, I think reflecting on what they've done and why they've done it is really quite powerful.
It is, yes, and it's very scientific, and I think that also acknowledges the value of different approaches.
Yeah.
And that's quite valid. Okay, so now I've now switched off that fifth one that you saw me construct. I'll go with the four original ones, and here we have our face. Here we have the normal and our incident ray, and then our refracted ray. Okay, and of course the angles that I'm interested in, and here's where colour really helps. I can talk about the angle of incidence as being the angle between the purpley or magenta line and the red line, which is the normal, and our angle of refraction being the angle between the green line and up this way, the green line and the normal. Let's just swing back.
It looks fantastic in all those colours with the image behind as well. It just looks amazing.
Yeah, and it just really helps the discussion that you can talk about which line. The red one. And of course, I mentioned before that the importance of having these on this square setting. So there's the capture of the. I've put two slides there. The image with the graph and the four functions, and here's our calculations. I've used the formula once using the gradients of the magenta line and the red line to calculate the angle of incidence of 45.3 degrees, and then between the green line and the red line, the angle of refraction being 29 degrees. Snell's formula gives me the refractive index of the block, which I think makes it look a little bit like a type of plastic or perspex. Good fun. I really like that, being an old physics teacher. I reckon that's a winner. And by the way, much more accurate than the first time I did this. I had the old light boxes set up in the dark, and we'd put marks on the paper, and kids would draw lines on it and get a protractor out to construct their angles. This is actually more accurate. There we go.